So for this example, we're going to go through some relative velocity transforms. So boxed off in red there, you'll see the principal transformation equations for both positions and velocities. And underneath that boxed off in green, you'll see the three-dimensional Cartesian coordinate system we're going to use. Our x is going to be east and west, our y is going to be north and south, and our z is going to be up and down. Now, the trick to dealing with all these problems is you're dealing with different frames of reference. So you need to be able to identify which frames of reference are present here. Now, when dealing with this, you can read through the problem. We got a surveyor up in the airplane. They're 300 meters above the ground and moving at 30 meters per second north relative to a point, which is where the external observer is sitting at. The person in the plane observes the deer 300 meters downwards and 20 meters east relative to her own position. And she also observes the velocity of the deer as being 10 meters per second west relative to her frame of reference. And what you're asked to find here is for this deer that this person up in the airplane is observing, what would you observe? And this is rather important if you're planning on doing any kind of surveying, right? If you're up in an airplane doing a, environmental survey, you're moving in a plane. So you need to figure out where things are relative to you. So, you can make a map of everything and stuff. Now, in order to do this, you need to identify three things. If you take a look at these equations, there's an O, an A, and a B in the subscripts. These O, A, and B are all referring to different things. The O is referring to the common object, the thing that both observers want to look at. In this case, both observers want to look at the deer. So our common object is the deer that they're both observing. Now, the A and B refer to the frames. Now, it doesn't matter which frame you call which. You're just going to label them. So here, let's say that frame A is going to be the person in the plane, and thus frame B is you, or the external observer, or whatever you want to call it. This is actually one of the hardest parts of this problem, is identifying and assigning a label to each one. Now, once you've done this, what I like to do is I like to make a chart based off of observation. This is just here to help you keep track of who sees what. So in this chart, we're going to label everything that's seen by frame A on one side and everything that's seen by frame B on the other side. These are all going to be vectors, and we're just going to go through. So we start off with the very first measurement we've been given is the airplane is 300 meters directly above a point on the ground. This is occurring according to the person on the ground. So for the quantity that this is, we're first going to give it a label. Number one, it's a position, so we're going to use X, and it is the plane, which is observer A, as seen by the person on the ground, which is frame B. That's how these subscripts are ordered. The first one is what are you looking at, and the second one is who sees it. Now, with this being said, we need to turn this into a three-dimensional Cartesian vector. This position is directly above them, 300 meters straight upwards. So there's nothing east and west, nothing north and south, and positive 300 meters because I'm going to use upwards or positive z to indicate upwards. And this is, of course, in meters, but as always, we'll leave the units out for now because unit conversions can always be done when you're finished. So that's the very first quantity you've been given. The second quantity you've been given is the exact same thing, but it is a velocity. It's seen by person B, and we're still looking at the plane. So just like before, we're going to look at a velocity, but we're again looking at the plane as seen by the external observer. Now, this velocity has nothing east or west, 30 north, and nothing up and down. And again, this velocity will be in meters per second, but for simplicity, we'll leave the units out for now. Now, we're going to go on to the third number that we're given. So if we take a look at the third number we're given, this is observed by the person in the plane, and they're looking at the deer 300 meters down and 20 meters east relative to their position. So the way that I like to sort this is I like to sort it by what frame. This is actually seen by person A, so we're going to put it in the frame A column. And this is a position. and it's a position of the deer as seen by frame A. So the first letter is what are you looking at? The second one is who's seeing it. As for the Cartesian coordinates, we're 20 meters east, so positive 20 in the x, nothing north and south, and 300 meters downwards from where we are. And again, I like to use positive for up in the z, so if we're going down, it's going to be negative. Now, secondly, the person in the plane also observes the deer moving at 10 meters per second west to their relative position. So this is a velocity. It is the deer, which is what we're looking at, as seen by the person in the plane. So this is VOA. And as for the Cartesian coordinates, it is west, which will be negative in the x, nothing north and south, nothing up and down. So with this, we have all the quantities we've been provided with, sorted by what we're looking at and who sees it. Now, our goal here is to find what position, we'll start there, would the external observer see the deer moving at. So if we grab our handy-dandy equation here, where we want the one that deals with position, and what we need to do is we need to figure out what we're looking at. Well, we're looking for the deer, which is O, the object, as seen by the external observer, which is position B. Now, the nice thing about making this chart is you'll notice you can line up the equal sign with the center of the chart. Everything that's on the left side is seen by person A. Everything on the right side is seen by person B. But this is something we can solve because we have XOA. It's 20, 0, negative 300. And this is equal to XOB, the thing we're trying to find, minus XAB, the plane as seen by observer B. So when we put these all in, we can actually solve for XOB, which is the animal as seen by us, the external observer. This can be done simply by adding 0, 0, 300 to both sides. If you do so, you will get 20, 0, 0, which, if you want to convert it, is simply 20 meters east. And that should make sense, right? The 300s cancel out because, we assume that the deer is on the ground, right? So the person in the plane sees the deer being below them. The person on the ground shouldn't. And the 20 meter east doesn't get changed by anything. Right? So again, it's a straightforward application of vector algebra. And that's how you would find the relative position. Again, it's just keeping track of what you're dealing with. Keep in mind, you can move things from one side of the chart to the other by multiplying them by -1 or by switching the signs around. Right? What I mean by that is if you have VAB, this is actually equal to negative VBA. And that's true for all of them. Now, we can do the same thing to find the velocity. Again, we're looking for how we see the deer. So at the end of the day, we are looking for VOB, the deer as seen by the external observer. And we can follow the same process. VOA is -10, 0, 0. This is equal to VOB minus VAB, which is 0, 30, 0. Right? That's a nice coordinate transform. So in the same fashion, we can solve for VOB by doing some vector algebra. This is done by moving this subtracted term to the other side, and we'll get -10 30, 0, which is a velocity that is moving west and upwards. So although this person in the plane sees the deer, or sorry, west and north. So although this person in the plane sees the deer moving west, when we're on the ground looking at it, we're going to see it moving both west and north. The reason the person in the plane doesn't see it moving north is because they themselves are moving north along with it.